Hey everyone, and welcome back. Today, we're stepping into the role of the wizard to completely demystify the Cambridge IGCSE additional mathematics syllabus. We're going to be looking specifically at subject code 0606 and tackling what is honestly one of the most fascinating and sometimes intimidating topics out there, the derived function. But we aren't just going to sit here and look at a bunch of math equations on a whiteboard. No, we're going straight to the source. We're exploring the actual examiner reports to see exactly how this is tested and what specific cognitive skills Cambridge examiners are desperately looking for when they grade your papers. Think of today's explainer as learning a magic spell. Exam strategies are essentially just structural frameworks, and if you can cast the right spell, you're going to unlock maximum marks. By the end of this session, we'll have a completely structured system so you can approach these exact questions with total confidence. Okay, look at this number on the screen, 15%. Take a second to really let that sink in. According to subject specialists, having a rock-solid understanding of the derived function accounts for roughly 15% of your total marks in the additional mathematics examination. That is a massive chunk of your grade. It's a number that completely reframes how we might want to approach our studying, right? I mean, prioritizing high-yield areas like this, it can literally represent the difference between two entire grade boundaries. We're talking about capturing a massive slice of the final grade here, just by mastering this one conceptual area. So here is our roadmap for today. First, we've got the 15% challenge. Second, mastering core principles. Third, the procedural framework. Fourth, the method mark strategy. And finally, top examiner warnings. Let's get right into it. Part 1. The 15% challenge, defining the goal. All right, so here is the exact definition pulled straight from the core syllabus requirements. It says candidates must, quote, understand the idea of a derived function. Sounds simple enough, right? But the really interesting part is what's hidden right there in the parentheses. An informal understanding of limit. No first principles required. You guys, this is actually a massive sigh of relief. It means we absolutely do not need to execute those lengthy, highly complex algebraic proofs associated with differentiation from first principles. You know the ones I'm talking about. Instead, the focus here is entirely conceptual. The examiners just want to see an intuitive understanding that a derivative essentially represents a rate of change. They want to know that you understand how the gradient of a curve behaves at an infinitesimally small point. Grasping that informal limit, really understanding the idea of a secant line gradually becoming a tangent, that is the real goal here. You don't need to mathematically prove it from scratch. You just need to know what it fundamentally is. Moving on to Part 2, Mastering Core Principles. What examiners want. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so this quote right here, straight from the Cambridge syllabus, brilliantly illustrates exactly what separates an average, standard answer from a top-tier, top-scoring one. It reads, top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. Let's break that down for a second, because it's packed with meaning. What does connected understanding actually mean? Well, it means seeing how the derivative relates directly back to the original function. It dictates the shapes of graphs, and it models real-world changes. And then there's that phrase, transferable to unfamiliar contexts. This is the ultimate test, guys. If we just blindly memorize steps, the moment the exam throws a curveball scenario at us, we're going to trip up. True conceptual understanding is what allows us to adapt our knowledge to entirely new, never-before-seen problems. And to test that transferable understanding we just talked about, the exam questions are specifically designed to target 3 distinct cognitive domains. First up is knowledge and understanding, basically knowing what a derived function actually is. Second is application. Can you actively apply differentiation rules to a given equation? But the third domain, this is where the real challenge lies, analysis. This boss-level domain involves taking a complex, multi-stage problem, pulling the whole thing apart, and figuring out exactly what mathematical tools are required to solve it. For instance, finding stationary points and determining their nature. That requires you to investigate the mathematical geometry of the curve based on evidence provided by the derived function. It's not just doing the math, it's analyzing what the math is telling you. Part 3, the procedural framework. Deconstruct, solve, evaluate. So how do top-scoring candidates actually approach problem-solving on the day of the exam? They do it systematically, using what's known as the deconstruct, solve, evaluate framework. Think of this as your core magic spell for the exam. Step 1, deconstruct. Identify the given information and meticulously extract the raw data from the text. Step 2, solve. Break the problem into highly logical steps and solve them systematically, one by one. Step 3, evaluate. Always check your final answer for reasonability and make justified recommendations based entirely on the mathematical evidence you just found. Now, expanding on that framework, we can clearly see the standardized sequence of processing that examiners are actively looking for. When you're using a derived function, we first identify the key elements, things like coordinates or gradients hidden in the prompt. Then, we apply the relevant principles. Maybe that means setting the derivative to 0 so we can find a turning point. Next, we execute the analysis, and we do this with incredibly clear working out. Then, we verify the results. Ask yourself, does a negative second derivative logically align with the maximum point on the sketch I made? Finally, present the answer in the appropriate format. Look, if a question asks for coordinates, providing both an x and y value ensures absolutely no marks are lost right at the finish line. For managing these intense, multi-stage analyses, the visual story method is a genuinely brilliant concept to explore. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, back to the visual story method. Instead of viewing a calculus problem as just a bunch of abstract numbers floating on a page, we can encode it in our brains as a connected narrative. Imagine the original function is a physical landscape. The derived function, that's your compass indicating the exact slope of the ground. Setting it to 0 is like reaching the very peak of a mountain, where the ground goes totally flat. And the second derivative, that's what checks whether we are standing on a peak or if we're down at the bottom of a valley. Attaching a visual, logical progression to these abstract mathematical operations can really aid your cognitive retention when you're under the immense pressure of the exam room. Moving on to part 4, the method mark strategy, saving your grade. And this brings us to a massively crucial examiner alert pulled straight from the reports. Listen to this. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. I cannot overstate this. The process is just as important as the final destination. The Cambridge marking criteria actively, enthusiastically award points just for demonstrating that you understand the procedural framework we talked about earlier. If we correctly identify the need to differentiate and we apply those rules perfectly, but then we accidentally drop a negative sign in the very final arithmetic step, sure, the final accuracy mark is lost. That happens. However, exceptionally clear, spaced out, easy to read working out secures the vast majority of the method marks for that question. Your working out acts as an incredible, life-saving safety net. Let's move into part 5, top examiner warnings, pitfalls to avoid. The absolute #1 mistake highlighted over and over in the principal examiner reports is that candidate answers are far too vague. When an exam question asks you to describe the behavior of a function, general mathematical descriptions will literally score you 0. We must counter this instinct by using highly specific context-driven details and rigorous professional mathematical terminology. For example, instead of writing something simple like the line goes up, we need to state the derived function is positive, indicating an increasing rate of change. That level of precision in your vocabulary demonstrates the exact evaluative skill the examiners are so desperate to see. A second major stumbling block we see involves critical comparative analysis. When interpreting relationships between different functions, the top candidates always show clear evaluative thinking. When a prompt asks you to compare, we have to identify both similarities and differences. You can't just pick one. You must use evidence derived straight from your function calculations to support those comparisons, and then draw evidence-based conclusions. An example of this would be evaluating why one specific mathematical model might be way more appropriate for a physical, real-world context than another, entirely based on the mathematical limits of its derivative. And the final warning from the examiners is all about presentation. There is a very stark contrast between ignoring required structures and meticulously applying correct formats. Look, if we extract information to build a derived function, the final result absolutely must match the exact format the command word in the prompt requested. If a question specifically, explicitly asks for an exact value, providing a rounded decimal is going to cost you marks, regardless of how flawless your calculus was leading up to it. Applying correct formats consistently from start to finish shows professional discipline, and examiners reward that discipline. So, to firmly encode this in our minds, here is a quick summary of the top 3 examiner warnings. 1. Answers are too vague. You must demand absolute precision from yourself. 2. Forgetting to check format and presentation. Always double-check the command words in the prompt before you move to the next question. 3. Answers lack specific context. Always tie your mathematical findings back to the actual reality of the question being asked. We've uncovered the immense power of method marks today, and we've laid out the entire deconstruct, solve, evaluate framework. So my final question to you is this. Knowing that your working out can literally save your grade, how will you consciously change your physical approach to your very next past paper? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Take these strategies, apply them to your revision, and we'll see you in the next explainer.